Okay. So we finished with test 3. We're on the home stretch. A few more topics. But we're actually going to stick with stress transformation. We're going to stick with, okay, these are my stresses at my original orientation, but what are the stresses at a different What are the stresses if I tilt my head, 15 degrees counterclockwise? What would be the normal stresses out of that cut? What would the shear stress be on that face? And so let's just go back to our stress transformation equations. So I don't know. Let's say we had a sigma x of 15 MPa, a sigma y of negative 25 MPa, and a tau xy of negative 20. So what if those were the stresses that we were given, that we maybe calculated, the stresses that we had? What would happen if we plotted them? All right, so here are my x and y axes. What if my x-axis was my sigma? And what if my y-axis, I'm actually going to put positive tau in the negative y direction, negative tau. We'll tell why. We'll see why we do that later. But anyway, sorry. Here we go. So what if I plotted normal stress versus shear stress? Right, normal stress versus shear stress. What if I plotted 15 comma negative 20? So right now we're going to stick with just looking at my x normal stress versus my shear stress. So if I plotted 15 comma negative 20, that would be, let's see, so 15, 5, 10, 15, and then negative would be up. That might be right there, right? 15, negative 20, my shear stress, comma, tau. All right, if I plug those into my stress transformation equations, and maybe I wanted the new stress at, I don't know, 10 degrees counterclockwise, my new point might be, I don't know, I could calculate them. We could go through this, we could calculate them, but my new point might be, I don't know, right here. And if I wanted to, another, what, about 20, 30 degrees counterclockwise, it might be right here. What if I kept on looking at new angles, at new orientations, my stress might look like this. This might be, it would be a circle. We could look at those, let me look at these stress transformation equations, and it would end up being a circle if we look at normal stress on the x-axis and shear stress on the y-axis. I don't know, maybe I gave that away here. That is Mohr Circle. Okay, so here we go. Mohr Circle is a graphical or a visual representation of normal stress versus shear stress at all orientations. All right, so maybe this was my starting point. This was my original point, but every other, and this is not a good circle, but that should be a good circle. Every other orientation is somewhere on this circle. This is Mohr's circle. Okay, this is Mohr Circle. That shows the stress at all orientations. So here's my original, maybe 0 degree orientation. And I don't know, this might be 15 degrees counterclockwise. What actually ends up happening, this right here is 90 degrees counterclockwise, and we could go all the way around. But a few things about Mohr Circle. The center of Mohr Circle, maybe right here, will be on the x-axis. Okay, so somewhere on the axis. Your Mohr Circle will be centered. It will be symmetric up and down, symmetric above and below the x-axis. It is not usually going to be symmetric about the y-axis. It is symmetric on the x-axis. The center is on the x-axis at sigma average. Okay, in this case, so in this one, the center will be at -5, 0. Center -5, 0. Okay, so the center of Mohr Circle will always be on the x-axis at the average of the normal stresses. All right, how about the size? How about the radius? Will be, well, it will be the distance of your original point to the center of the circle. Doesn't that make sense that the radius would be the distance that any point is away from the center of the circle? So the radius will be the distance from, I'll call it the original point, to the center of your circle. We'll talk about this later, but how would we find this distance? Well, we could figure out the height and the base and do a squared plus b squared equals c. Let's do that real quick for this one. Well, actually, I don't have this value. I have something here. Maybe the height would be 20. The base, let's see, if that number is at 15 and that number is at -5, the base would be 20. So this is a 20, 20, take the square root of those to find the radius. Okay. Another thing, notice I said over here is 90 degrees counterclockwise, but it's almost like I took this and I rotated it 180 degrees, didn't I? So another thing about Mohr Circle is 1 degree in real life equals 2 degrees on Mohr Circle. All right, 1 degree in real life equals 2 degrees on Mohr Circle. And then one last thing, sigma y will be on the other side, opposite side of the circle from sigma x. All right, so if, and it's sort of negative sigma y. Sorry, negative tau. All right, sigma y will be opposite on the side of the circle as sigma x. So if this right here is sigma x, that right there would be sigma y. If I've rotated it some and I've calculated here's my new sigma x prime, then my new sigma y prime would be on the other side of the circle. Would be on the other side of the circle. Which makes sense because my x face and my y face are 90 degrees apart. So they're 180 degrees apart on Mohr Circle. So there's some things about Mohr Circle right there. Okay, Mohr Circle is the location of all of these points for that, all the different orientations of the stresses right there. Okay, now Mohr Circles will look completely different. I mean, you might have one Mohr Circle that's all over here. You might have one Mohr Circle that is huge. You might have one Mohr Circle that is all over here. They will be different just depending on your original stresses. But they will all be centered on the x-axis at the average stress, the radius. You can find the radius. 1 degree in real life equals 2 degrees on Mohr Circle. And sigma y is on the opposite side of the circle. And then we'll get to this, but where are the principal stresses on Mohr Circle? Let's think about this. Where are the principal stresses on Mohr Circles? Well, what are the principal stresses? The principal stresses are the maximum and minimum stresses that will ever occur, right? The principal stresses are the maximum and minimum stresses that will ever occur. So what is the maximum normal? We're talking about normal stresses. What's the maximum normal stress that will ever occur? Well, that's just the right side of this circle. What's the minimum? That's the left side of that circle. This right here is your normal stress sigma 1. This right here is your normal stress sigma 2. Hey, what's the shear stress when you have the principal stresses? 0. Isn't that my y-axis is 0? You know, my y dimension is 0. That makes sense. How about the maximum shear stress? The maximum in-plane shear stress would be either right up here or right down there. Okay. And hey, what is the normal stress at this location? The average, right? Which we already knew. A lot of these things we already knew. Okay, all right, so let me give you some steps that I like to do when I'm drawing my Mohr circle. Okay, so we're going to take this page and bleed on to the next page. And let me tell you, why are we drawing this? We're drawing this because then we can use Mohr's circle. Now we can use Mohr Circle instead of all of these equations, because all of these equations are inside of Mohr Circle. They're hidden inside of Mohr Circle. We're not going to have to memorize these equations. We're not going to have to use these really complicated equations, because we're going to be able to use Mohr Circle, and everything we know about circles and triangles and base height, radius, we can use those instead of our stress transformation equations. It'd be really cool. All right, so to draw Mohr's circle, this is how I do it. Step 1, draw the axes. And draw sigma positive on the x-axis, and draw tau positive down. Draw tau positive down. We're going to draw tau positive down so that counterclockwise in real life is counterclockwise on the Mohr circle. That's why we draw tau positive down. So draw the axes, and then plot your original reference point. Plot your reference point. You know, your original point. Your starting point. Plot sigma x tau xy. So don't worry about sigma y just yet, but plot. So in this case, I plotted 15, negative 20. You know, 50. So whatever this is, and whatever that is, plot it somewhere. Where is it? It might be over here. It could be here. It could be anywhere. Just plot your reference point. Step 3. Plot the center of your circle. Where? At sigma average. When I'm sigma average, I'm taking the average of sigma x and sigma y. The average of your normal and shear stresses. How do you find the average of two numbers? Take those two numbers divided by 2. So here I knew if I took the average of those, add those two together, divided by 2, the average was negative 5. So I could plot my center on the x-axis, right? On the x-axis at negative 5. Your center might be it could be anywhere. Could be 0, could be negative 20, negative 70, positive, but your center is always going to be on the x-axis. Okay, then once you have 2 points, you can find the distance between those 2 points. This is going back to high school. Okay, but it's very easy to make a mistake here. Don't make a mistake here. Find the distance between those 2 points is the radius, right? The distance between those 2 points is the radius. So step 4, calculate the distance, or calculate the radius, which is the distance between those 2 points, between the reference point and the center of your circle. Now, like I said, don't overcomplicate this, but be very careful. If, one point, my starting point is right here, and my center is right there, then calculate this distance as the radius. Calculate that distance as the radius. So, let's draw some numbers on here. So maybe the center was at -15. And maybe this value is, let's see, what could this be? Maybe 25, comma, positive, let's say 20. 25, comma, 20. All right. So to find that distance is the hypotenuse of a triangle. So let's find this length right here. Find that length and find the distance between here. All right, so that length right there is 20. That length right there is 20. But this base right here is not 25. Okay? This base, do you hear that? And let me reiterate that, because this will be the most common mistake. This base right here is not just 25. That 25 is from the axis, from the origin. Right? These are from the origin. This base would be 25 and 15. Right? 40. Okay? Let me reiterate that. If this is my starting point was 25, 20, and my center was at -15, then this radius would be a squared plus b squared equals c squared. This side is 20, but this side would be 40, right? And I don't want you to memorize equations, but the equation here would be 25 minus average squared plus tau xy squared, take the square root. Now, don't memorize that. But that, is how you calculate the radius. That is how you calculate the radius. Okay, so here are our steps. Draw the axes, plot the starting point, plot the center, and then you've got it, right? Then you can find the radius right there. Okay, this is the book's picture. I'm just going to keep on going with our notes here, and I'll go to step 5. All right. And so my next step, the way that I do this, is I start at the center and plot 4 points, plus and minus the radius in the x direction. Plus and minus the radius in the x direction. And plus and minus the radius in the y direction. See if this makes sense to you. Okay, once I know where the center is, maybe the center's right here. And maybe my reference point was right here. I don't know where my reference point was. Okay, so if this was my starting point, and this is my center, and I have found this distance, let's say it is 16.4, then I go here and I go to the right, 16.4. I go to the left, 16.4. I go up, 16.4. I go down, 16.4. All right, you see what I'm saying? So start at the center, go left and right, the radius. Go up and down, the radius. Right? Doesn't that make sense that if you know where the radius is? So that gives you some points. Then you can kind of connect and kind of try to draw. I'm not going to make you draw with a compass or a protractor or anything like that, although you really could, and it would be helpful. Some other teachers would have you do that. Now, mathematically, be sure this makes sense, right? Starting at your center. So let's say my center was at 10 right here. So I would go all the way over here to 26.4, right? And then I would start 10. I would subtract. I would go to the left 16.4. What would that be? Negative 6.4, right? So start at the center, go left and right, the radius, go up and down the radius, and then connect the dots. So 6, connect the dots to form your Mohr's circle. Connect the dots to form Mohr's circle. Okay. Now, next step, we want to calculate theta p. We want to calculate theta p. We want to calculate the orientation that the principal stresses are. Okay? And so this angle, the angle to the x-axis, the angle to the x-axis, this is going to be the x-axis or the positive or the negative x-axis, but the angle to the x-axis on Mohr Circle is not theta p, not theta p, not theta p, 2 theta p. The angle, this angle right here would be 2 theta p, or in this case, this angle to positive would be 2 theta p. The angle to the x, positive or negative, x-axis, is 2 theta p. How can you find that angle? Well, you can do tangent of this triangle, right? Opposite over adjacent. So I would say, okay, 2 theta p is opposite over adjacent. Opposite over adjacent. Now, again, I don't want you to memorize this, but the opposite is always going to be your tau. Let's do, tangent of 2 theta p is opposite over adjacent. Your opposite is always going to be your tau, xy. And your adjacent, that would be the sigma x, how far sigma x is away from the average. How far sigma x is away from the average. Now, that was, let's see if that was my theta p. My 2 theta p right here. Yes, sigma x minus sigma average, we could change sigma average to sigma x plus sigma y divided by 2. And so yes, that the everything that we're doing on this circle are these equations, or were these equations. Okay, so from the circle, you can get 2 theta p Make sure to divide it by 2 to get theta p. And number 8, we can calculate principal stresses which we probably already kind of had this calculation, but do you see that our sigma 1 is sigma average plus the radius? Sigma 2, sigma average minus the radius. Here, I'll go and come back. All right, do you see that sigma, that right there is the average, plus and minus, that right there is the radius. That right there is the radius. Okay, last thing, or let me squeeze this on here. We have already calculated tau max. That's the radius. Tau max is the radius. If we got on that clipboard, we could see that tau max is the radius. And maybe one, I don't have this in my notes here, one out here. Theta S is in Mohr Circle 2. Where is it? It is the distance to the vertical. 2 theta S would be the distance to the vertical. 2 theta S would be the distance to the vertical. Then a couple of things. We know that theta P and theta S are 45 degrees apart. It kind of makes sense that theta P and theta S on Mohr Circle are 90 degrees apart. On Mohr's circle, 2 theta S is to the vertical, the angle from vertical. Okay, this is very messy, but let's go back over this. Let's reiterate this. Okay. All right, so Mohr Circle is a plot of all the different orientations. Draw the axes, plot your starting point, and plot your center. The center is on the x-axis at the average. Then, if you got 2 points, then the distance between those 2 points is the radius. Once you've got the radius, start at the center and go radius right, radius left, radius up, radius down. And then you've got 4 points plus your fifth, your starting point, so you've got 5 points. Then you can kind of start to draw a sketch, a real, hopefully it's nicer than mine, a real circle. Theta P is on your Mohr Circle, but it's 2 theta P, and it's the distance that your starting point, your starting line, is to the x-axis. The principal stresses are here and here, right? Which, so how do you actually already calculated them? You took the average and added the radius. You took the average and subtracted the radius. Tau max is at the very top and very bottom. You know, what's the maximum the y value will ever be. And theta S is also on Mohr Circle. It's the angle that your starting line is from vertical. So one thing is just to be careful. Let me write this in purple. Be careful about measuring. Are you measuring from the axes, right? Your origin, or from the center, right? For instance, if you've got the base of that, triangle, well, you don't need to just take that 25 that was measured from the origin. You need to look at from the center to the point would be the base right there. Okay, but these values are from the origin. You know, if I got some numbers right here, and it was -20, -15, those are from the origin, right? Coordinates are always from the origin, but many times these bases of these triangles are from the center. Okay, I think a lot of this will get cleared up, hopefully, as we do some more of these Mohr Circle problems, okay? All right.